we'll start something related to Fourier transform called Laplace transform. Laplace transform is the last thing they did with transformation, the recent one, and more general than Fourier transform. And I'll tell you why now. And it's really simple and easy. I like it even more. But there are applications for Fourier transform, especially in communication. But because I'm automatic control person, so I like Laplace. The people who work in automatic control, they use Laplace a lot. All their work Laplace. People use communication, image processing, they use Fourier transform. What is the difference between Fourier transform and the other one? If you look at Fourier transform, you multiply the signal by e to the power minus j omega t, and then you find Fourier transform. Laplace, it is very similar, but we do not multiply by e raised to imaginary part only. No, it can be, we call it like e power minus st. Instead of you say multiply by e to the power minus j omega t, no, it's e to the power minus st. And s is a symbol, and it means equals sigma plus j omega. So it has a real part and imaginary. So that's more general. I'm not multiplying the function or the signal by e to the power minus j omega. No, e to the power minus s, and s is equal real plus imaginary. So it's more general. The beautiful thing about Laplace transform, if you want to solve, and I'm sure you did in math, you solve differential equation. Did you have in math how to solve differential equation yet or not? Yes. And I remember when I had the course, you got to find the characteristic equation first, so you can find the transient or a complementary solution, and what other one? There are two solutions in adding complementary part, right? And particular solution, yeah. And you find the roots and just and there are many cases if it has like imaginary complex, it's just headache. Laplace not like that. Why? Because Laplace converts differential equation to algebraic equation. So we are solving algebraic equation. One shot, and you get everything, the total solution just in one shot. That's very simple. They used a lot in systems to represent the systems. And convolution also, you don't make the integration, you just multiply. Like what we did in Fourier transform. You multiply x of s times a h of s. Okay, let's see how can you find this transformation, and then we'll do in the end application. We are going to solve the differential equation. We are going to look for system input and find the output, and how can you control the system. So and Laplace was like, I think, a French mathematician. It's the name of the guy that did that. He had many transformations.
Laplace is like a more simple version of Fourier?
Not simple. No, it's more general, generalized Fourier transform. Because the other one, e power minus j omega, minus j, imagine. But this one, e minus s, or minus s. And s is not imaginary, it's complex, real plus imaginary. So it's more general. Okay. Let's see how we'll do Fourier transform. And the same thing, you'll have table. But I'll show you how you do it in the beginning, how to use the integration, and then after that you have table to use. Very similar to Fourier transform. The integration of Laplace look like that. First of all, if you have x of t and you make Laplace transformation, called L, not F, Laplace transformation, then you will have x capital also, but not function of omega, function of what? Variable s, yes. And s is a complex. How you get it? Well, x of s is equal the integration from minus infinity to infinity, exactly like you are writing Fourier transform. X of t e to the power, not minus j omega, minus S T. That's all. You replace omega. You replace J omega by S. So Fourier transform is a special case of Laplace transform. Okay. Let's take example how we apply this. And we'll take our favorite example, the exponential. Let's say x of t is equal to e to the power of minus at. A is a positive number. Ut. So it's the same one that we did before. So if this is the time and this is the function, so it looks like that. And it's given a should be greater than 0. So let's do the integration. The integration will be, we'll say x of s equal to the integration from minus infinity to infinity, e to the power minus at ut. No, yes, that's right. E minus st dt. Ut, what does mean ut? Means from 0 to infinity. So before, so the ut is defined like that. That's ut. It's 1 when time greater than 0 and 0 before that. So I'm going to change the integration from negative infinity to 0. That will be 0 because before that will be equal to 0 according to that. To infinity, and then I will leave that out. That will be the all right. I have that. How you integrate that? When you're multiplying exponential by exponential, what you do to the power of the exponent? Add. That's right. So we'll say the integration of 0, infinity, e, I take minus here, a plus s t dt. What's the integration of exponential? Let's say e to the power of minus, say alpha x. What's the integration of this one? That would be e minus alpha x over minus alpha, right? So I'll do the same thing. To be e, that's my alpha. A plus s t divided by minus a plus s. And the limit of integration, infinity 0. So what you'll do to get rid of the negative here? Oh yeah, that's right. You switch. Okay, I thought you were asking. Minus a plus s t divided by a plus s without the negative, and then I switch the limit 0 infinity. Now I will have it like I have 1 over a plus s, a common factor, and then I substitute e power 0 is equal 1 minus e to the power infinity minus infinity. We minus infinity we equal 0. So the answer is 1 over s plus a. So Fourier transform for exponential function e power minus at times ut is equal 1 over sa. So if you say, for example, what's the Laplace for e to the power of minus 2t ut, what you'll get? 1 over s plus 2. Right? A is equal to. Let me show you now something very interesting. If I want to find Fourier transform of the same function, what's the answer? 1 over a plus j omega, right? So if you know Laplace, you can get Fourier. Replace s by j omega. That's the trick. And if you know Fourier, you want to find Laplace, replace j omega by s. So if you put s is equal to j omega, so Fourier transform of the same function, it just would be 1 over j omega plus 2.
So it was 2.
Because it's a special case.
If the s is equal to 2, equal to 2j omega?
2 j omega.
Like if the S was 2, would it be equal to 2 j omega?
No, I don't understand what do you mean by 2?
You said S is equal to j omega, right?
Not S equal j omega. If you want to convert from Laplace to Fourier transform, because we said that Fourier transform special case of Laplace. Why special case? For simple reason. S is equal sigma plus j omega. That's S. Has two parts, real and imaginary. J omega, or I mean Fourier, that's Laplace. Fourier has only j omega. So if you want to convert from Laplace to Fourier, just put sigma equal to 0. Yeah, and replace S by j omega. You get Fourier. That's it. And the same thing. If you want to, if you know Fourier transform, you want to get Laplace, replace j omega by S. All right. So that's an easy way. Okay. What about the unit step? Let's take another example. How to find the Laplace of unit step? That's example 2. X of t is equal u of t. To find Laplace, what's u of t? It means it's equal 1 when t greater than 0 and 0 when t less than 0. So to find Laplace, we'll do the same integration. We'll say x of s will be equal u of s equal the integration from minus infinity to infinity u of t e minus st dt. U of t will be equal u of t will be equal to 1 only when it starts from 0. So I'm going to change it to 0. So I'll say Laplace of the unit step will be equal to the integration from 0 to infinity and 1 e minus st dt. That will be equal to the integration will be e minus st over minus s, and then I have infinity to 0. I will do the same thing. I will say e minus st over s, and then I flip. So I have e power 0 is equal to 1, e minus f is equal to 0 over s, so it's equal 1 over s. That's the Laplace of unit step. We can go and do many things, example like that, but I mean, it's very, as you see, it's very simple and very easy. And there is a table, and I already put the table in the formula sheet for Laplace transform. Okay, I'm going now to show you an interesting example. Let's find Laplace transform of the function e to the power of j omega t ut. How you get this? No, that's you do that once you get the once you get the Laplace transform. I didn't get it. It's in time domain. You don't do this time. Let me clear something. So this j omega by s, right? That's if you have Fourier transform. Is it Fourier transform? It's a time. So how can you find this? You'll be able. I know I can make quiz, but you can do that in 1 minute. Think about it. Anybody? Oh, let me give you a hint. We just did find Laplace transform for e to the power of minus at. Did we do that or not? Replace. Yes. It's a special case of A. What we did, that's why I want you to pay attention. It is nothing difficult in this course. It's just, I mean, you have to be like, wake up. That's all. That's it. Yeah. So if you have something, we got e to the power of minus a t ut. We just did that, right? And we found what was the Laplace? 1 over s plus a. 1 over s plus a. That's why I use that in Fourier transform. I'm still using, so you can remember this example. Now, if you compare that by that, j omega t by, if you compare, you say minus at equal j omega t. T cancel t. So what's a? Minus j omega. So replace the result here that you have a by minus j omega. So you will have, now I can say Laplace of e to the power of j omega t ut equal to 1 over s minus j omega. That would be the answer. Right? And I do integration. Why do integration? Yeah. Don't do integration except if you don't have something in the table. And the table has many, like Fourier transform. Let me ask you another question. Easy, like this. Huh?
Who shall be the judge of that?
No, I'm doing these examples in sequence for a reason, and you will see now the results. Let's just. I'm sure all of you will know how to do this one. I'm positive. I want to find for Laplace transform for e to the power of minus j omega t ut. Yeah, exactly. Instead of one, all right, that's good. I know that. I know you're good. Wait for the third one now. So Laplace transform for e to the power of minus j omega t ut is equal to 1 over s plus j omega. So now what we got, when you have e j omega t ut, you get 1 over s minus j omega. If you have e minus j omega t ut, you flip this the sign. So always the sign opposite to the power that you have. Actually, I was not doing that for this reason. It's coming now. Example 5, it's the one I want to start, but I did it steps. So example 5. Find Fourier Laplace transform for cosine omega t ut. Of course, if I started this example by this one, you will not like it. It will be kind of fun. Do you like to make this quiz? Can you see the answer? Or you just work together? Work together. Okay. You should be able to do that without integration. You should. Using the information of the previous 2 examples, you will be able to get it easy. So I want somebody to give me an idea. What do you think? I give you 1 minute to think and you tell me that's what we're going to do. Yes, go ahead. Can you give me this? Oh, no, I don't use Fourier. No, I don't use Fourier. I would use Laplace table and your information about the complex number. These 2 pieces of information will help you to find the answer. No, don't think about it like that about omega. Like I can ask you what's the cosine 10t ut. It's just a value.
Oh, okay.
All right. Let me. I mean, because usually we say cosine omega t, but the cosine number, omega is not, is not, yeah, it's not for you, yeah. You can say it like, as I said here, if you want to find Laplace for cosine AT, for example. Let me just, I mean, I got not to be confused between Fourier. I think I want to find Laplace for cosine AT. All right? There is no omega. I mean, it's not that frequency. It's just, it was the frequency of cosine, but I'm saying it's a number, like 10t, 5t, 5t. So how can you find Laplace for cosine AT? Yes, yes, that's right. He didn't hear you, just didn't see anything. Yeah. How can you use the last or the previous two examples to find the Laplace for cosine? You know that cosine, all right. We know that what's the E minus JAT Laplace for this one? Can you give the answer now? You know that we did that 1 over S plus JA, right? What is Laplace for EJ AT UT? 1 over S minus JA. How can you use the two pieces of information to find Laplace of cosine AT? Euler. Yeah, Euler. I see in some faces somebody say Euler, so what's Euler? I see it, I swear I see it. Do you know what's Euler? Euler? Nobody knows? Or no? Yes, that's right. Yeah, okay. So you know Euler. This guy will stay with you all the time. So cosine AT is equal to e to the power JAT plus e minus JAT over 2. We did that. And sine, if you want to find sine, Laplace sine, you can do the same thing. Sine AT is equal to e to the power of JAT minus e minus JAT divided by 2j. That's, I mean, the two Euler form. One for the cosine, one for the sine. So now I need the cosine one, and I know how to find the Laplace transform. I have it here. So I can write that the Laplace of cosine AT UT is equal to Laplace of e to the power of j AT UT plus Laplace, because it's linear transformation. You can do that. E minus JAT UT, and then when you get them, divided by half. I'm just using this formula. Do we have it? Yes. We have it. 1/2. What's the Laplace of e power JAT? It's 1 over S minus JA. And for this one will be the opposite, S plus JA. All what's coming, just simplification, algebraic simplification, will be equal to half. I will have a common denominator, S square plus A square, and then you have in the top S plus JA plus S minus JA. JA cancel minus JA, so you have 2S in the top, S squared plus A squared, and 1/2. Cancel. So Laplace of cosine AT UT is equal to S over S squared plus A squared. And this formula given in the table. You can get it from the table directly. But I'm just showing you how can you find Fourier transform using properties. And I use the first property, that linearity. You can find that if you have a function, complicated function, you can break it down into the sum of 2 functions or 3 functions, and then find each one separately and then add it. It's a linear, as a linearity problem. Next week, we don't have lab, but you are coming to the lab. I'm not assigning you lab. We'll give a lecture because we're behind and took a long time in the Fourier transform. So I will continue Laplace. I'm making more examples of Laplace so you can understand. Okay. There's something important that people in control, automatic control, use, not in control, in systems. How do you know the system is stable or not stable? But first, I mean, I want you to understand, and I know it's not, I mean, I showed you this stability, but I'm sure in physics and mechanics in an electric system, you know stability, right? You know stability. What does it mean, stability in general? Yes? No, I don't to tell me definition and mathematical way. I want just the physical meaning of stability. When I say the system is stable, what does that mean? It doesn't switch between states. No, it can switch. No, it can switch between states. It's stable. Yeah. Okay. So what? Well, let me show you something interesting. Because this is my field control. How to find system stable? I'll give you not control system. Simple thing. If you have a ball like that, and there's a ball inside, we are saying this is an equilibrium position. True? Steady state, it's equilibrium position. Let's say, and you did disturbance. Somebody just come by the tips of the finger, just force it to go. What will happen to this ball? Move up, right? Move up, and then it'll move down, going other side. It will be just going from one side, and the oscillation is decreasing. In the end, go back again to the same equilibrium position. That's a stable system. So the stable system is like, I mean, if you have a disturbance, external disturbance from outside, affected this object, and after the disturbance is removed, and the system after a while go back to the equilibrium position, it's stable. What about that? If you have the same ball like that, you put it like that, and you put the ball in the top. That's equilibrium position, staying there. By the tip of your finger, just do it like that. Believe me, if you stay next to this ball for 1 year, the ball never go back again. Never. So that's unstable. And stability is not only an object, even human being. You find everybody was stable, but maybe some incident, disturbance in life happened and affected the person. If he can go back to his normal character, normal personality, normal status, he is stable. But if you speak out, he's not stable, right? Human beings, society, economic system, all the like disturbance always happen. So if the system is stable, after removing the disturbance, it go back again to it. So it's not like only for object. No, I believe everything happened to object, to human being, to society systems. So how can you use Laplace to find the stability of the system? They said that if you have the transfer function of the system, what does it mean? Transfer function. Transfer function, if you remember when we talk about the Fourier transform and all things, we said this is a system and it has an input and it has an output. If now we are working with Laplace, we are not going to use this. We're going to use Laplace S domain. So you have X of S and you have Y of S and you have H of S. And then you look here for the system H of S. That's the system. How to know stable or not? Very simple thing. They said that just examine the poles of the system. Poles of the system. And if the poles they have negative real part, it's stable. What does it mean, poles of the system? Let me show you one, like something like that. S plus 1, that's H of S, example of 1. H equal S plus 1, S minus 2 over S plus 3, S squared plus 2S plus 2. That's we call it transfer function of the system, which relates the input to the output. Usually it's a rational form like that. If you want to find the roots of the top part, the roots of this one, we call it zeros of the systems. If you want to find the roots of the bottom bar, that we call it the poles of the system. So now if I ask you what are the zeros of the system, find the roots. What do you mean find the roots? Just make it equal to 0. So you find S is equal to -1 and 2. That's the zeros. Zeros do not affect the stability of the system. The poles affect the system. What are the poles of the system? That's the zeros, and that's the poles. Solve this one. So you have -3, and then you might use your calculator at the second order to find the roots. Then you find it's equal -1 plus j minus 1 minus g. So these are the poles. Is the system stable or not stable? The rule is look for the real part of the poles. If they are negative, it will be stable. If there is if all of them negative and one is positive, the real part is positive, it's not stable. So this system, I would say yes, it's stable. Why? Because I mean that's -3. -1 plus j, I concern only about the real part. So that will be stable. And the whole explanation of that. When I learned that in control system, they said the rule. But I mean, they never told me why. Why when it's negative real part be stable? Then I start to make writing programs for system different, see the response. So I found something interesting. What is the Laplace for e to the power of minus t? We just did it, right? It's equal to 1 over s plus 1, right? How we sketch this one time domain? But what about if I say what's Laplace for e to the power of t? 1 over s minus 1, right? How we sketch this one? So I found out when you have exponential decay, Laplace is equal 1 over s plus 1, and the root or the pole is equal to -1. But when I have e to the power t, I found it's not decaying. Actually, it's increasing, going to infinity. And then I find the pole is equal to +1. So I found the reason. Because when you have decay function, if you have disturbance, the effect will decay, will go away. But if you have it a positive exponential, it means it's increasing. It's getting more unstable. So I said, okay, that's why they have. So for every math, the numbers, the negative, the sign, when I search, I found, I mean, always it has reason. It's not just like, I mean, rule, that's negative be stable, positive be unstable. I will stop here and then I will continue and have lecture again next week. Yeah. And in the lab, I mean, we'll do that.